So here I want to kind of give you a nice introduction to the scientific method and what that is. Again, this course is designed to allow students to kind of explore what that scientific method is and then allow us to kind of apply those principles to the world of sport nutrition. So let's take a look. So, what is science? Science is knowledge obtained by observing natural events and conditions in order to discover facts or formulate laws or principles that can be verified or tested. So, again, when we think about science and the scientific method, it's all about using logic in order for us to understand what is most likely to happen in various scenarios. So, how does the scientific method work? So, the scientific method is used every day by scientists to investigate problems to answer questions. So, the first thing we want to do is we want to ask a question. We're going to do some background research. We're going to construct what's called a hypothesis or like an educated guess as to what we think will happen. And then we're going to figure out how to test our hypothesis. And then once we have tested that hypothesis, we'll take the information that we've gathered and analyze our data in order for us to draw conclusions about that information and then report our results and determine whether or not our hypothesis was correct. So let's use an example here to help us kind of understand. So number one, ask a question. Maybe we are interested in knowing, does caffeine consumption improve someone's time in a 5K run test? Okay. So first thing we would do if we were curious to know the answer to that question is to do some background research. So we want to look into the research and figure out, okay, have other researchers looked at caffeine? Have other researchers tried to determine whether or not caffeine can be helpful or not for 5K running? Maybe we've seen some results where they use a small amount of caffeine and that wasn't effective, but a larger dose was effective, or we see that caffeine was effective for longer distance races, but maybe not for 5K. So we're going to do some research, see what else is already out there so that we know how we can best set up our experiment to understand how to answer this question. Okay, next we'll construct a hypothesis. Well, based on what we've already seen in the research about shorter and longer races and about certain dosages of caffeine, we might guess that 200 milligrams of caffeine can improve our performance by 10 seconds in a 5K distance or something along those lines. Okay. Next thing we'll do is test the hypothesis. We have to get subjects. We have to administer the protocol. So maybe that involves them taking 200 milligrams of caffeine. 45 minutes before their race, and then we see what their race times are in comparison to a control trial. Okay. Next, we're going to take our data and we're going to analyze that data and draw some conclusions based on our findings. And then we will be able to report our results and see whether or not our hypothesis was correct. So when we think about this, when we state the problem or questions, the problem identifies what it is that you want to find out. For our example, we said we wanted to know whether caffeine would be advantageous for a distance runner to take or not. So we want to develop a clear statement defining the problem. We want to know whether or not caffeine would enhance or hinder or have no effect on our performance. We want to make sure our problem is narrowed and specific enough. So something like, does caffeine improve sport performance, isn't specific enough for us to really know whether or not that's going to enhance performance, because when we say sport performance, that can mean so many different things. So we need to be really specific so that we can make sure that our question is testable. Okay. We can state the problem in the form of a question. So how does caffeine affect 5K run performance? Or what is the effect of 200 milligrams of caffeine on 5K run times, or something along those lines? So again, you can see we want to create a hypothesis, which is a formative explanation for what we think will happen. And again, it's important that this is testable. So we can't just say like, does caffeine help sport performance? We want it to be much more specific so that we can make sure that we can actually determine whether or not it's true. Okay. How do you test a hypothesis? To develop a test, we need to understand whether our results will support or not support our hypothesis. And that's what our experiment is. Okay, so we must run this multiple times. So it's not enough for, like, if we wanted to know if caffeine improved 5K performance, it's not enough for you to just test yourself and say like, oh, well, I had a Red Bull and I ran a 5K and I ran it really fast, so caffeine must help performance. So we need to have multiple subjects in order for this study to work out or be able to run this multiple times. We must only have one independent variable, and this is the factor that we are testing. Okay, so in our example here, the independent variable is caffeine or no caffeine. And we must have two setups. We have an experimental setup and a control setup. So for example, if you run the 5K race and you have a Red Bull beforehand and you run really fast, okay, we still don't know how fast you run without caffeine. So we need to have a control trial so that we know how fast you run without caffeine, and then an experimental trial where we can figure out how fast you run with the caffeine. Other factors that are important when we think about utilizing the scientific method are the variables. So we have variables are characteristics with quantitative values. So we have independent and dependent variables. So our independent variables are manipulated or changed. So those are the things that we're manipulating as researchers or experimenters. Okay, so again, we said caffeine in this example would be a great variable for us to manipulate or change. And this will be represented on the x-axis. Okay, the dependent variable is what we're measuring. So in our particular example, our dependent variable was 5K performance or 5K time. Okay, so that's what we're measuring after we've manipulated our subjects by giving them caffeine. And this will be represented on the y-axis. We also want to have some research controls as well. So control conditions are a standard against which other conditions can be compared in a scientific experiment. So, as we mentioned, it's cool to see like you can run a fast 5K if you have Red Bull, but we need to have a control condition so that we know how fast you are without Red Bull or without the experimental trial. Okay, so again, we need to have that control condition in order for us to understand how to compare ourselves. Okay, so we need to have careful consideration of the design and data collection in order for us to produce accurate results and ensure that the changes in the dependent variable are due only to changes in the independent variable. So what are some other factors that we can try to control when we think about setting up a solid research plan? So we want to think about the characteristics of the subject. So the sex, age, body size, smoking and dietary status, and then appropriate selection of subjects are all important. So for example, if we wanted to know if caffeine was going to enhance our running performance, would it be super effective for us to ask football players to run the 5K with caffeine or without caffeine? The answer is probably no. That's not a great, or it's not a super appropriate subject population because the football players aren't going to care, right? Like they're never going to run 5K in a normal part of their sporting event anyway. So it doesn't really like give them any type of information that's useful. So we need to think about choosing appropriate subjects based on what it is that you're testing. Now, if we wanted to look at like a pre-workout and how that would affect like our 1RM, then yeah, let's use the football players because that would be a little bit more appropriate based on what might help them in the long run of their performances. Okay. Other things, you can think about body size as well. So, especially in sport nutrition, we think about caffeine. I gave the example of 200 milligrams of caffeine. Again, if I'm a 105-pound female distance runner, 200 milligrams of caffeine is pretty darn different than if I have a 260-pound male football player. Again, those are going to affect those populations pretty differently. So we think about body size. That's another factor to kind of keep in mind. The design of the experiment. So we can do a control group, as we talked. We can have a placebo group and something known as crossover design. Okay, so the control group, we kind of talked about having a control condition where we wanted to know what those people's 5K time was before they used the caffeine. Okay, placebo group would mean that we gave them a product that they didn't know if it was caffeinated or not, because again, if you believe something's going to help your performance, it probably will. So a placebo kind of takes that out of the equation. Maybe we give you like a sugar-free drink for one trial and a caffeinated drink for the other trial, but you don't necessarily know which one's which. Okay, and then crossover design is important to help us to prevent people from what's called the learning effect. And maybe you're thinking to yourself, like, what do I need to learn in terms of running a 5K? But I guess my question would be, if you knew what your time was for the 5K the first time you did it, would you try to beat that time the next time you did it? And the answer for most people is yes, they are going to, just innately try to improve the second time they do something. Again, you're going to learn a little bit in terms of pacing, or learn a little bit in terms of maybe what the course is like and things like that. So through a crossover design, we'll have half of our population use caffeine first and half of them do a control trial first, and then we'll switch. Okay, so that's where that crossover design comes from. And that would allow us to help to prevent that learning effect. Okay, we'll have standardization of procedures. So again, we want to treat all of our subjects equally. We want to have calibration of our equipment, and we want our results to be reproducible. And the way we make our results reproducible is through standard procedures, and we want to make sure we document all of that. So one way to think about the research process is in a cyclical way. And so it starts with curiosity. So again, I wanted to know if caffeine would allow me to improve 5K times. So I created a problem. Does 200 milligrams of caffeine before a 5K race improve running performance for the 5K distance? Next, we look into the literature or look into the research to determine whether or not research has been done kind of similar to this particular project. Next, we'll create a hypothesis that we believe that 5K time will improve approximately 10 seconds per trial for the 5K if they use caffeine. Next, we're going to design our research protocol and come up with our variables. So our independent variable is caffeinated or non-caffeinated, and our dependent variable is 5K time or 5K performance. We find our subjects, and again, we want to make sure our subjects are appropriate. So we would try to find some distance runners or endurance athletes that would find this information useful or applicable. We'll collect our data. We'll do some analysis of our data, so kind of understanding what's happening from a data perspective. We'll draw our conclusions, report, and then that will turn us back to curiosity. So if 200 milligrams of caffeine did result in improvement of performance, would 300 milligrams be even better, right? So again, you can kind of see how this process continues on in this cyclical way based on what it is that we find in our research.